All right, so this next example is meant to be more of a justification for the result that we're going to be using in this section. Okay, so there is a result that makes things a lot easier. But I want to go through this example to sort of build up the reasoning behind the result that we're going to end up using. All right, so in this example, I'm going to take the long way. I'm going to take the long way to the result, and then we'll generalize at the end, and then you'll have a nice little formula to use. So I just want to point that out before I get started on this to just to let you know that the approach that I'm taking in example 2 is not necessarily the approach that you're going to take in the problems that you're going to do in the homework. It's just meant to sort of build up the justification for the result. And we're going to come up with a nice little formula, and then you'll just be able to use that. Okay? But so that's the purpose of this example. But before I get started though, I'm going to define some variables. I'm going to call the n, my variable n, the number of trials. So n is the number of trials. Number of trials in a binomial experiment. All right. P is what we're going to call the probability of success. Probability of success. However we want to define success. Whoops. Hang on. Success. S-U-C-C-E-S-S. All right. And Q is going to be the probability of failure. Probability of failure. Failure. Okay, however we want to define failure. Now, P and Q are related to each other, right? Because it's, the outcome is either going to be a success or a failure, because if it's a Bernoulli experiment, you only have two possible outcomes. And if there's two possible outcomes, then these P and Q have to add up to 1, which means that Q is essentially the complementary probability. So we can get Q just by subtracting P from 1. Okay, so these are complementary events, right? The success and the failure are complementary events. Complementary events. Either one or the other is going to happen. And so we can find Q just by subtracting P from 1. All right, let's take a look at example 2. All right, we have a fair die, and it's rolled 3 times, and we want to compute the probability of obtaining exactly 1/6 in 3 throws, 3 rolls of the dice. All right, so based on our, actually, why don't I keep this up here for now? I'll just keep this up here. And so, let's see. So n is the number of trials. And in this case, we're rolling it 3 times. So n is equal to 3. P is the probability of success, right? So we're defining success to be rolling a 6, right? That's what we're interested in, is rolling a 6. So the probability of that, if we define that as success, as 1/6, which means that Q, it has to be 5/6, right? There's a 5/6 chance of not rolling a 6 on any given roll. All right, so we've got N and P and Q. And now what I'm going to do is I'm going to draw a tree. Now, on these types of problems, I'm not going to draw a tree on every single problem. But again, like I said, I'm setting up the justification for the formula that we're going to come up with. All right, so I've drawn a tree to illustrate all the possible outcomes of three rolls of the dice, right? Or a die, 1 die. All right, and these are all the possible outcomes, and I've also put the probabilities on there. I'm just putting it in terms of P and Q for now, because I want to generalize my result. So the probability of success. Again, I'm defining success to be a 6. So this is really 3 6s in a row. Is just going to be P times P times P, so P cubed. The probability of success, failure, right? So this would be 2 6s and something that's not 6, would be P squared Q. Okay, I'm just multiplying these probabilities along the branches of the tree, just like we've done before. So the probability of success, failure, success, that's this outcome here, is just going to be, again, p squared q. And then the probability of success, failure, failure, right, is just going to be p times q, which is pq squared. All right, so we're just going to keep going and just show the probabilities of all these possible outcomes of the roll of three, rolling this die 3 times. So this branch represents the failure, success, success. So we're going to have p squared q, right, because q times p times p. This one is failure, success, failure, which is going to be, okay, we got 1 success and 2 failures, okay? And then this one is going to be failure, failure, success. So we've got 1 success and 2 failures, right? So pq squared. And then the last one is failure, failure, failure. And the probability will be q cubed. Now I can make a little probability distribution for this too. I could make a little table with the number of 6s. So that's the outcome that we're interested in, number of 6s, and the probability of those different outcomes, right? So essentially the number of 6s is my random variable, and it can take on 0, 1, 2, or 3, right? We could get 0 6s, 1 6, 2 6s, or 3 6s. So now we can take a look at our tree and find those probabilities. The probability of 0 6s would be down here, right? It's the failure, failure, failure. So the probability of that is q cubed. Now there's several different ways that we can get 1 6, right? 1 6 and 2 non-6s, right? So let me just highlight those. Let me highlight those with yellow. So we could get it this way, or this way. In all of these cases, we have 1 success. And so basically we could add up all those probabilities. So it's basically pq squared 3 times. So 3 pq squared is what we would get if we added those all up. What's the probability of getting 2 6s? Well, let me highlight those. So this is 2 successes and 1 failure, right? So again, I have 3 of those. So it's 3 times p squared q. And then the probability of getting 3 6s would be this p cubed. All right? That kind of looks, it doesn't look like a superscript. I'll make it look like an exponent there. All right. So there's our probability distribution. Now I could plug in p is 1 6 and q is 5 6, but I'm not going to do that yet because I want to generalize. So what's the probability of exactly 1, right? Exactly 1. We want exactly 1 6. Well, I'm going to write that as p, my random variable is x, this is essentially x right here, equals 1. All right, so I can just see that from my table. I've got 3 pq squared. Okay, so now you can see where the pq squared comes from, but the 3 might not be so obvious. Again, I want to generalize. So let's think about how many ways there are to get 1 success and 2 failures. So think about that as success, success, failure, or some arrangement of those letters, right? So essentially we're just asking how many ways can we arrange that letter, those letters, right? So we have 3 letters, and 2 of them are indistinguishable. So we would divide it by 2 factorial. That would give us the number of letter arrangements. But that is actually the same as 3 choose 1. The combination 3 choose 1. 3 things taken one at a time. Because we've essentially got 3 trials and we want to choose one of them, exactly one of them, to be a success. And so that's where the 3 is coming from, 3 ways. So if we want to generalize, then essentially it's the number of trials. It's C and choose X, whatever we're looking for. whatever the value of x is that we're looking for, right? In this case, it was exactly 1/6. All right, so 3 choose 1 is you have 3 trials. We want exactly one of them to be 6, so it's n choose x. All right, so let's keep going here. So let's now generalize that result that we got. All right, so we have n trials. Let's say we have n trials, and we're looking for the probability of x successes. All right, which means that if we have x successes in n number of trials, we have n minus x failures, right? Because if it's not a success, it's a failure. So we have n minus x failures. So if we're looking for the probability of some number of successes, and we have x of them, we have x successes, and then we have the rest are just going to be failures. So we have some number of failures, and there are n minus x of those. The probability of that is going to be p to the x q to the n minus x. All right. Now that's for that particular arrangement of successes and failures. So we have x successes and n minus x failures in that order. Okay. But if we're looking in general for how, we got x number of successes, then we can think of that SSSSS and so on, FFFFF and so on as a letter arrangement. So let's think of that as a letter arrangement. So there are n factorial over x factorial n minus x factorial ways to arrange those letters, okay? Which is the combination of n things taken x at a time. It's the same thing. So there are that many ways to arrange the letters. So ways to arrange these letters that I'm pointing to here. Actually, those letters. Okay, those xs's and n minus x f's. All right, it's just a letter arrangement problem. But it's the same as, because there's only 2 possible outcomes, it actually ends up being the same as a combination. So we're just we're just choosing x of the n possible, or n trials to be successes, and then the rest will automatically be failures. All right, so if we want now the probability of exactly x successes, what we end up with is, we've got this many ways. We have the combination of n things taken x at a time. We have that number of ways to arrange these successes and failures. And for each one of them, the probability is going to be p to the x, q to the n minus x. All right, and that's the result I was referring to earlier when I started this video. All right, that's the result that we're going to use. So anytime you have a Bernoulli trial, you can use that result to calculate the probability of exactly x number of successes, whatever we want to call x. If in this case we were interested in getting exactly 1/6 out of 3 rolls of a die, right? So in this case, well, I suppose I could finish I never did actually finish the problem, right? So we're interested in probability of x equal 1. So that's one success. One success is defined to be a 6 being rolled. And so we're going to take the combination of 3, n is 3, right? Choose 1, and we're going to multiply times probability. So the probability of success is 1/6 to the x, which is 1. So I should probably say 1, 6 to the first power, times 5/6, 2, and minus x, so that's 3 minus 1, which is 2. Okay. Now, when I put that into my calculator, I get 0.3472, so about a 34.72% chance that we would roll exactly 1/6 in 3 rolls of a fair die. All right, so the result here is summarized in that little box, and there's a couple of definitions here, a couple of vocabulary things here. A binomial random variable is just a random variable representing the number of successes in a binomial experiment. Okay, so in this case, we had the number of 6s was our random variable. And a binomial distribution is a probability distribution that is associated with a binomial experiment. Okay, so that's actually the title of this of this section, is the binomial distribution. But so if we calculate all of the probabilities of all of the possible outcomes and put them in either a table or in a histogram format, that's a binomial distribution. It's a probability distribution that's associated with a binomial experiment. All right, well, I will meet you in the next video.